In this section, we are going to look at the different types of graphs that you may experience on the ACT. You must not only be comfortable about how to read and interpret graphs, but also understand what the general shape should look like if you were asked to plot a graph given data. You must be able to transfer back and forth between a data table and a graph on the test. All right, a graph is a great way to represent the relationship between two variables. The independent variable, member, is the one that's controlled by the experimenter. That's going to be graphed on the x-axis. The dependent variable, the one that changes as a result of what has changed, is graphed on the y-axis. It's important for you to be able to interpret a graphical relationship and graph data that's given to you in a table. Okay, so we're going to go through 5 different shapes of graphs. Our first one is just a horizontal line on your graph. And as you can see here from the written relationship, as the x variable increases, the y variable is going to stay the same. So there's no relationship between the variables. Let's just do a real quick example. On the right-hand side here, you're going to see a position versus time graph. If we were to put some numbers on this, you can see time here is on your x-axis, position is on your y-axis. So let's just put a few numbers on here, maybe like 1 second, 2 seconds, 3 seconds. And maybe on our position axis, maybe 1 meter, 2 meters, 3 meters. Okay, now let's take a look. Where's this object after 1 second? If we go to 1 second, we come up, we see that the object's at 3 meters. 2 seconds, again, we come up, see where it's at. It's again at 3 meters. 3 seconds, we come up, and again, it's at 3 meters. So we can see that the position of the object does not change as time increases. So something like this, the object would not be moving. All right, our second type of graph is going to be a graph with a positive slope on it. So if you look at the description here, it's going to be as the x variable increases, the y variable increases at the same rate for each unit of x. And we talked about in the first section that y would be directly proportional to x. So let's do again an example with a position versus time graph. If we were to again put some numbers on here, maybe 1, 2, and 3. And maybe our starting position for this one would be something like 1 meter. Okay, so as we can see, it's going to be a straight line. What that means is it's going to go over 1 second, maybe it goes up 1 second. So after 2 seconds, that object would be at like a position of 2 if we read off the graph. After 3 seconds, if we come up, it would be at like a position of 3. Okay. But the y variable is changing consistently with each unit of time. So each second, this object is gaining 1 meter in its position. Okay. Another thing you can note here is the slope of this line. So if you take a look at the slope, the units on the slope, the rise is in meters. And then the run is here in seconds. So if you look at just the units is going to be meters per second. Therefore, the slope of this line is going to tell you the velocity. So for our example that we did here, the slope of that line would be 1 meter per second. And so the object would be traveling at a speed of 1 meter per second. Okay, the third shape you may encounter is almost like a curved shape here. What that means is as the x variable is increasing, the y variable is decreasing, or y is inversely proportional to x. A good way to look at it is look at the slope, how it changes over time. So like this slope at first on our graph here to the left, it's very steep. But if you look at the end, the slope is not near as steep as what it started at. So let's go over here and do an example on the right side. Here's a position versus time graph. And again, I'm just going to put some numbers on here just to make it easy for us to see. I'm going to go by 1 second again. Okay, now let's say this object starts at a position of 10 meters way up here. And we'll maybe just go by 5. So I'm just going to put a 5 here, and then 0 would be down here. Okay, after 1 second, if I could maybe project up here to the graph and read over, maybe that would be at a position of maybe 7. Or let's say 8. Make it easy. Okay, so in the 1 second, this thing traveled 2 meters in the first second. Let's do the same thing. Let's go to 2 seconds. and project up to our graph and read over. Now that looks like about 7. So look at what happened to the distance it traveled in the next second. It was at 8 and it went to 7. So that would be a distance of 1 meter. If I would do it again for maybe like 3 seconds, 3 seconds would be maybe 6.5. Okay, and that would be a distance of 0.5 meters. So you can sort of see what's happening. The first second, that object traveled 2 meters. The second second, it traveled 1 meter. And the last second, it only traveled half a meter. So what's happening is, at first, if we look at our slope, it's not traveling as fast. At the end, it's traveling much slower. And again, if you look at the slope as it goes along, the slope is decreasing along this line to the very end. Okay, the fourth type of graph is almost like a J-shaped curve here. What that means is as the x variable increases, the y variable is increasing at greater rates each unit of x. And again, the best way to think of it is look at the slope at the very beginning compared to the slope at the very end. And you'll see at the very beginning, the slope is not very steep. At the end, the slope is very steep. So let's do an example here on the right-hand side, again with a position time graph. So if you look at this one, as the time is increasing to the right, the position is also increasing. But it's not increasing at a constant rate because it's not a straight line. So you can see that the position is actually going to be increasing at greater rates each unit of time. So again, if we were to put some units or labels here on our axes, I'll go by ones again maybe. And maybe we'll start this one at like 4 meters. And we'll just go by 2s. All right, so after the first second, we can see at 0 seconds, if we were to put that on here, this object starts at 4 meters. After 1 second, that object hardly moved. It's just a little bit above 4. After 2 seconds, maybe it's at 6, and then 3 seconds, it may even be above 8. So if we look at the distance it travels again, in the first second, it travels a really small distance. Let's just call this maybe half a meter. In the second second, it maybe goes from 4.5 meters to 6 meters. Maybe it travels 1.5 meters. And in the last second, it goes greater than 2 meters. So you can see as time goes on, this thing is covering more distance for each unit of time. And the way you could look at that again is look at your slope. Here it's not very steep. Up here it's extremely steep. So that thing's not going very fast at first, and then at the end it's going faster. So that thing would be speeding up because the slope would be getting steeper. Okay, and the fifth scenario you may get is as the x variable is increasing, the y variable is increasing at smaller rates each time. And again, the best way to look at this is look at the slope. At first, it's really steep, and as you go along here at the end, it's not very steep. So our example here on the right again, a position versus time graph. As time goes on, position's increasing, okay, but it's not increasing at the same rate the whole time. If we were to put numbers on here again, all right, so at 0 seconds, that object maybe starts at 2 meters. After 1 second, if I project all the way up, it's at almost 6 meters after 1 second. So this thing went from 2 meters all the way to 6 meters. That would be a distance of 4 meters. Let's see where it's at after 2 seconds. Follow 2 up. Now it looks like it's about 8 meters. All right, so it started at 6, and now it's at 8. Now it traveled only 2 meters. So for this one, you can see as time's going on, the position is actually getting less for each interval of time. So something like this, an object like this, would be slowing down. Okay, one thing you may be asked to do on the ACT test is draw a graph for yourself and maybe draw a best fit line. Most of the time they'll give you stuff in a data table. A best fit line is sort of like a rough estimate about how the independent and dependent variable are related. You're going to have to use a line sometimes to extrapolate data or extend the graph to make a prediction. Okay, so let's do one example. First you want to plot the points, and then you want to draw a best fit line through the middle of the points. You can see how several points are going to lie to the left of the line and several points are going to lie to the right of the line. So let's say you have a data on maybe a chart or something like that, and you plot your points like this. All right, then your best fit line, you want to draw through the majority of your points, okay, which I have drawn on here. You can see on the right side, there's a good majority of points. On the left side, there's a good majority of points. So it's sort of like an estimate, rough estimate of the data. One major question on the ACT test is to predict what maybe the y value would be for a larger value of x. So let's say we have a value of x that may be way over here that we don't have in our graph yet. What you're going to want to do is extend this best fit line further than what you have it right now. Okay, extend your x-axis to whatever number you guys need. Then what you can do is extend your y-axis. Again, you guys want to note what units and what rate your y-axis is increasing by. And then you can just look at that x value, read up, and then read over to see what y value would correspond to that x value. In conclusion, you should be extremely familiar with how to plot a graph and use it to your advantage to answer the questions on the ACT. It will really benefit you on the test.